The title of Professor Guglielmi talk is Solving Integro-Differential Equations, Modeling Pharmacodynamics.
Yeah, so it's a jump with respect to previous talks. Well, first of all, I wish to thank all of you for organizing this meeting, which I found very nice, also for the heterogeneity of the talks, and naturally the organization of the project, which has brought so many very interesting contributes. I think it was an extremely successful experiment idea. So please interrupt me whenever you wish. I will give you some results on a problem that we have started to face recently, and which is inspired by the modeling that is done in the pharmaceutical industry in ambit of effects of drugs in terms of the dynamics and kinetics, of course, in patients. So this is a joint work with Ernst Steyer from Geneva, with whom I have had a long-term collaboration since 25 years. So let me start with some history. So more or less in the 90s, Ernst wrote a code which was called Rado 5, an implicit solver for stiff systems of ODEs, even large systems of ODEs, and in particular also for implicit ODEs. So, for example, differential algebraic problems. And this was in a sense a challenge because many were skeptical about the fact that you can integrate large systems of differential equation in an implicit way efficiently. But the code was very successful. It is still a very successful software. And in 2000, so more or less 10 years later, we started to develop together a project extending stiff integrator to differential equation with discrete delays. So differential equation with discrete delays are functional differential equation where the right-hand side addresses the solution in the past through a pointwise functional. So essentially, for example, like in an epidemic, you ask for the solution at a certain precise instant in the past, for example, 5 days ago. And these codes were used in academia, Rado 5 before a lot, but seemed confined there. And to our surprise, in 2019, we were contacted by ICON, which is a multinational producing software for pharmaceutical industries. And they started to use, I would say, intensely delay models in the simulation of drugs. So in particular, in the simulation of the pharmacokinetics, the pharmacodynamics. So pharmacodynamics resembles a bit chemical kinetics, except of course that this is related to the interaction with the human body, which makes the problem extremely more complicated than, say, an isolated simple chemical reaction. And delays play a very important role here because the effect of a drug is typically delayed of hours or even of days. And sometimes this is also not known a priori, so modeling the delay is a big part of the model. Clearly, this is a reductionist approach, is reduced, but this is the starting one in the research, at least in these pharmaceutical companies that make research and use of these models. So Radar 5 that we developed were confined to discrete delays, even many, but discrete. What about distributed delays? For example, when you have a distribution, a probability density. So in the right-hand side, you have a dependence on this whole solution in the past through an integral, and the kernel models a certain distribution, a certain probability density. Okay, so let me introduce the class of problems that I'm interested in. Here M is a mass matrix. In the simplest case, you can think that M is the identity. Y is the state vector, which represents the state of the modeled system. And you see that the function depends not only on T and Y, which would mean essentially an implicit system of ODEs, but also on the solution in the past at the time t minus tau. Tau here is a fixed positive delay, which might also be a function of time or of y, which would make the delay state dependent and much more difficult numerically to integrate. But in any case, tau is a specific positive number or non-negative number in general. The new part, which nor Rado or Radar 5 are able to integrate, is more in the field of integro-differential equation, is this terms I, this integral term, which is the convolution of a kernel K and the function G of the state Y, of the solution Y. So in pharmacodynamics, in pharmacokinetics, there are several important kernels, in particularly the gamma distribution, the Pareto distribution, the Gaussian, the doubly Gaussian. So we are here interested to play with some of them, in particular those that are most used in this community. One remarkable aspect, at least analytical and numerical also, is that K is not in general smooth. It can have an integrable singularity at the origin. This is the typical case of the gamma distribution, where you have t to the minus alpha, and alpha is a positive number, real number. Okay, so what could one do with an equation like that? Clearly, one could be tempted to discretize I, to discretize the integral by a quadrature formula. This would give you a problem essentially just with discrete delays, many. So essentially at any grid point that you use in the discretization of the integral 0t, you would have a tau I, which corresponds to that. And so you should address the solution in the past at discrete instant. But first of all, this would give you a very high number, very large number of terms if the step size of discretization of the integral is relatively small with respect to the support of the integral. And second, when you have a singularity in the kernel, so if at t you have a singularity, then this becomes very risky, also in terms of stability and accuracy. So we wanted to adapt, so not to start a new problem, to see whether we could adapt what we had to this kind of systems. Okay, so for this kind of problems, even if the delay, the red term is absent, we know what to do in the implicit setting. So for stiff problem, for differential algebraic problem, here I omitted the matrix, the mass matrix N for simplicity, but you can always include it. In this case, no, we don't know, and we in particularly understood quite immediately that it was not meaningful to have a priori discretization by quadrature of the integral term. So there exists an extensive literature on the differential equation. We are certainly not the first to study this kind of problem, but there are a few things that have to be said. First of all, there are no codes in general that are able to couple discrete and distributed delays together. They don't exist. Stiff problems are also challenging, and in particular, a very important aspect when you have a stiff integrator is to change the step size, to have step size control, in particular when you have a transient layer, when you have singularly perturbed problems. It's very important, or multi-scale problems. It's very important that the step size is not constant in time. I'm speaking about the step size in time, even if this problem can arise from discretization of PDEs often. And this is usually not done in the literature, where typically, also in the very famous convolution quadrature, which was introduced by Lubick in the 90s, the step size has to be constant to exploit the properties of the method. So here I give you two kind of distributed delays, two probability densities that we address. There is an article on the Journal of Pharmacodynamics in 2018 of Xuhua Hu, who is a researcher at Certara, which is a big company developing software for pharmaceutical applications, which analyze more or less, is a review on all kind of densities that they consider. And this is the very well-known gamma distribution. In particular, here alpha and kappa are positive. These constants are in a way that the integral of k is 1, which is, of course, the normalization for the probability density. And so here the point is how to deal with t to the minus alpha, and also how to deal with the fact that there is a weak singularity. Another one, which is also described in a recent article in the Journal of Pharmacodynamics of 2020, is this so-called Pareto type 1 distribution, which is in a sense similar, but here there is no singularity because kappa is 0 in a right neighborhood of the origin. So in this case, still the constants are such that the integral is 1, but there is no singularity. So this is a little bit different. In a sense, in this second case, there appears this beta that separates the behavior in this interval in a non-smooth way, which is a sort of discrete delay in the kernel. Okay, so what I will shortly discuss here today, and I will be extremely, I will avoid to give you many details because I have no time for that, but I just wish to pass you some ideas on the problem of integrating this kind of equations, is to replace essentially this kind of integro-differential equation by systems of differential equations or delay differential equation, which approximate them in a, let's say, suitable and possibly optimal way. This has been possible by the method that I'm explaining you in the next few slides. And in particularly, when you play with the first kernel, the gamma, you end up with the system of ODEs. So you can use an implicit ODE solver. This system is stiff, even if the original problem is non-stiff, due to the approximation that we do. So it's essential to consider an implicit integrator. And in the second case, due to this beta, we end up with the system of delay differential equation with the delay tau, it was called before, which is equal to beta. And so in this case, we can still make use of radar 5 with essentially minimal modifications. One important point in terms also of this project, that sometime the number of ODEs, even if you start from a single ODEs or of a reduced number of ODEs, the additional number, the augmented number of ODEs or ODDs that you add to the problem in order to approximate the integral term is big. And so the integration might become slow. So for this, it's extremely important to exploit the linear algebra. The linear algebra, and in some cases also to exploit, if possible, high-performance computing facilities, in particular, if your problem comes from a discretization of a partial differential equation, for example, with no local effects, where these integral terms, these distributed terms, appear in the proportion of many. For example, any one associated to any grid point of the discretization in space. This would be a challenging high-performance computing problem, which I will not discuss in this talk. So let me give you, so here, don't be confused. This is just to give you a model which was developed by a researcher at Bayer. But don't be confused. So even if you don't look at it, it's not important. This is just a typical kinetical model of really similar to the kind. So the kappa are kinetical constants. It models in a very reduced form, so in a compact ODE form, integral differential form, the chemotherapy-induced suppression of granulocytes. So A is the drug, which obeys a differential equation which could be solved independently from the others. And then you have the precursors of the granulocytes and the circulating granulocytes that are modeled in this model in the human body. So here I is modeled, and this modeling came essentially from regression models from data available from patients. Is modeled by a gamma distribution, and in particular, the parameters kappa and alpha has been estimated based on statistical models. So when we have this, I want to show you the solution that you can get. I give you just a reference of parameters for that. And I would like just to observe two aspects. One is that differently from discrete delay, which exhibit jumps in the derivative at multiples of the delays at breaking points, here the solution is moot. And the other very important point is that if you look at y of t, so the granulocytes, you see that you have a transient layer. So at 0, y0 jumps very close to 0 in a very small time, so in a very fast time scale. So there's a transient layer, and then it goes to a smooth solution. So here is essential to use a very small step size in the transient and to enlarge the step size after the transient. So we need a numerical integrator which uses variable step size. So these are the aspects that I wanted to mention. As I already told you, even if the problem is non-stiff, but in this case, in chemical kinetics, in pharmacokinetics, the problems are originally stiff. In any case, doing applying the method we propose, the problem always becomes stiff. So we ask to use implicit ODEs, solve to be implicit. And when you have an ODE, so from now on, I forget the discrete delay. I only work on ODEs because with the gamma distribution, it's enough. So when you have a system, an implicit systems of ODEs, one of the bottleneck, so why would you need high performance computing or fast solvers? Because if the system is large, you have to solve the Runge-Kutta equation. In particularly, in this case, in Radon, you have a collocation method at Radon nodes. That is the basic numerical process. And when you solve this by the Newton method, of course, the solution of the linear system, so the inversion, the solution of linear systems, so the computation and the solution of linear system with the Jacobian is the most demanding part. So in the end, the linear algebra is always the bottleneck of this kind of processes. And we have to solve linear systems where the Jacobian has a kind of structure which is shown in the bottom line of this slide. So it involves the Jacobian of F with respect to the state variables and the matrix N. So how do we play? So here I enter in the main part of my discussion. This is the main point. Assume that we are able, and this will be the next step, we are able to approximate in some sense the kernel. The kernel in this moment is this gamma distribution, so it's t to the minus alpha, by a quasi-polynomial. What is a quasi-polynomial? A quasi-polynomial is an entire function, which is a linear combination of polynomials multiplied by exponentials. So in the simplest possible case, you can think that these polynomials are degree 0, so are just constant. And you can think that the simplest possible problem, which is already quite interesting, is the approximation of the kernel by a sum of exponential, a finite sum of exponential with exponents gamma I. So what's interesting in this? What's interesting in this is that if you have that your integral term in the integro-differential equation. This applies, for example, also to fractional differential equation, to non-local operator, where the dependence is through an integral term. Then this, of course, is approximated by replacing the kernel by this summation, so by this quasi-polynomial. And so these variables, Zi, are just these integrals of powers of t minus s, integer powers, multiplied exponential. Now, if you define Zij in this way and you differentiate it, then you get a system of ODEs. Then you get ODEs. So you can completely forget of the original integral term, replace it by a sum of exponential multiplied by polynomials, add the differential equations, and then essentially this is an oblivious method. So the integral dependence is forgotten. You add a number of additional augmented differential equations, and everything is completely solved in the setting of ODEs. What's the problem here? If kappa is originally in this form, then the problem is equivalent to a system of ODEs. If the problem is not originally in this form, we have to find a good way to represent kappa, to replace kappa, to approximate kappa by a quasi-polynomial. Okay, in this case, let me be fast. So in this case, you add the ODEs for the Zij, which allow you to treat this integral term in the right-hand side. You have now an augmented system of ODEs with a super vector, which is y, the original state, and all these z vectors associated to the expansion. And then you have an augmented system, which is a system of ODEs with a very special structure. You see, you have this original dimension d, and then you have additional couplet systems of dimension m1 plus 1 and m plus 1, when this m1, mn are the degrees of the polynomials. So what's the main problem? That sometimes the dimension d is small, but the sum of the dimension m1 plus mn is large. So you pass from a small dimensional problem to a large dimensional problem. So is this value, is this convenient? Is this meaningful of what we are proposing? Well, it is meaningful if we are able to efficiently solve the linear equations, so the linear system, the linear algebra, which is the real bottleneck in the Newton iteration applied to this kind of problem. In particular, and this is what I wanted to mention before, the gamma, so the exponents of the expansion in quasi-polynomials, can be very large. So you have this exponent minus gamma I with gamma very large. So the augmented system is stiff, independently of the original problem. Even if the original problem is not, in terms of the variable y, this is stiff. So the use of an implicit integrator is not a choice, is necessary. So there are no possibility. One cannot use an explicit integrator. Okay, so as I mentioned before, we have to solve a system which now is an augmented system of this kind. Can we do it efficiently? Well, this is the point. This system that I've written before has a certain spatial structure. The global linear system has the dimension d plus n, and typically n can be much larger than d. So the number of additional ODE is much larger than d. The whole matrix has a very special structure. The structure is this one, is an arrow. So you have this block diagonal structure. J is the Jacobian of F. J1, J2, Jn are these simple b-diagonal matrices, which are essentially minus gamma I, the identity, and a lower diagonal matrix. They are associated to every block Z, associated to every polynomial. And then there are these matrices B and C on the that makes the arrow, so on the first column and on the first row. And what's interesting is that they are rank 1. So to make it short, all of this can be solved very efficiently by the linear algebra, because the complexity is not cubic, as with the full linear algebra Gauss solver, but it's just linear in n. So exploiting this special structure, rank 1 arrow kind, we are able to obtain a solver which is only linearly, has a complexity only linear in the number of additional. So even if we add 10,000 ODEs, then we don't really have a 10,000 to the cube flops in the solution of the linear system. Okay, so this is, I don't give any detail of this, I don't have time. Let me go to the end. So how do we approximate t to the minus alpha? Here is the main idea. So t to the minus alpha is indeed the Laplace transform of z to the alpha to the minus 1, apart from this constant, which is gamma of alpha. So we can express t to the minus alpha in integral form, and in particular in real integral form, not in complex form. So we don't have to do a contour integral to approximate, but a real integral. If we just replace the independent variable z by the exponential to s, just with this simple change of variable, we have this integral from minus infinity to infinity of an analytic function. Now it's intuitively clear what to do. So for analytic function, the use of the trapezoidal rule gives you spectral convergence. So we have the hope, by discretizing this integral, which is the real Laplace transform of t to the minus alpha, to get, with a relatively small number of exponential term, a good approximation. So this is the step. This was proposed by Belkin and Monzon in 2010. Apply a trapezoidal rule to approximate this integral, and in this way, t to the minus alpha. So clearly, this is a series. We have to truncate it, and we have to choose h in an optimal way to approximate the integral below a certain, so in order to control the error, the approximation error. And then we have to study how this approximation error has impact in the integro-differential equation. So this is a result that you find in a very nice review paper by Treffet and in Acta Numerica in same review in 2014, but it comes back from the theory of Rabinowitz. So the relative error that you obtain by approximating this integral by the trapezoidal rule, the relative error is bounded by c to the c alpha, and this c alpha, you see the denominator, there is the exponential in 1 over h, so is exponentially fast with respect to h. So you have spectral convergence with respect to h. In order to bound below a certain tolerance epsilon, the relative error, so c alpha, you have to choose the step size in a certain optimal way, and we choose a, these are just technical manipulation, in a way to get maximal h. And then the final step is to truncate at minus infinity and plus infinity the series in a way to get a finite summation, still by controlling the error in the Q's by epsilon. Epsilon could be 10 to minus 8 or a given tolerance. So when you have this, in the end, you have that the relative error that you have replacing by this finite summation t to the minus alpha is bounded by 3 epsilon, where epsilon is chosen by the user. We have developed code which are available in our websites, and epsilon is a constant which can be decided by the user. And in the end, we have this. When we have this, we can replace t to the minus alpha in the integral term and get a system of ODEs. So here, just a numerical experiment where we applied the trapezoidal rule. We computed the error in the approximation in t to the minus alpha, and we compared the h, which is in the abscissa in this picture, to the theoretical h, which we computed by our a priori estimates that I didn't detail. And here you see that with epsilon 10 to the minus 5, with the relative error 10 to minus 5. If h is less than 0.78, we obtain the required accuracy. The theoretical estimate, that the one would be used in the code, is 0.70. So there is a 10% pessimistic overestimate, so quite acceptable. Okay, so with this, maybe I can skip this. So this is the gamma distribution. If you have a negative value of alpha, of course, then you don't have any singularity, any weak singularity. But the idea in this case could simply be to write t to the minus alpha as the product of t and t to the minus alpha minus 1, and then reapply all the theory that we have developed to t to the minus alpha minus 1 that now would be negative. In this case, since we have this t, we just would have linear polynomials in t in the previous expression. And so we would have that the blocks in the linear algebra would be 2 by 2. Anyway, let me go to the numerical experiments to emphasize also the performance of this. Let me take this example. So with these parameters, this is just a very educated example because we know the exact solution, which is t over 2. So we can compute everything exactly in terms of error. So we take an integration window 0.50. So the exact solution is 25 at the end. And we choose a tolerance in the time integrator, which is 10 to minus 8. And so we want to see what happens when we vary epsilon. Clearly, this is the tolerance in the integrator. So the numerical integrators try to keep the local error below 10 to estimate the local error before tolerance, below 10 to minus 8 at every step. So what do we expect? If epsilon is bigger than 10 to minus 8, then the integral, the t minus alpha, is bad approximated. So we expect that the error that we have in the final solution is due to the fact that we don't approximate sufficiently well the integral term. And this is what appears in the last columns. Instead, if epsilon is smaller than 10 to minus 8, then the final error is due to the numerical integrator, to the tolerance that the numerical integrator used to control the local error. And you see, indeed, that after 10 to minus 8, the error computed in the final solution stagnates at 10 to minus 8 at the tolerance. So this behavior, the error here is the relative error, is exactly what we would expect. You see in this table m and n. So we have one equation, and to this equation, we add m plus n ODEs. So you see, we start from one equation, and we add, in the last case, 133 plus 127 equations, so 260 equations. So from 1, we go to 260, which is a lot. So let's do a final experiment with the real model, the one of myelosuppression, and let's try to understand the linear algebra. So I consider the standard application, which is by default the Gauss solver, and I compare it with the fast solver that is linear in complexity with respect to the number of augmented equations. And this is my last table. So look, for example, with the tolerance 10 to minus 8. These are 3 ODEs, if you remember. This myelosuppression model is 3 ODEs. We add more than 1,000 ODEs. So the system is 1,000 by 1,000, more or less. So this is the linear system that you have to solve many times. It is already challenging. If you use the standard solver, you have 10 to the 2 seconds, 200 seconds, 3 minutes. But with the fast linear algebra, you have 10 to minus 2 seconds. So you have a 10 to the 4 reduction of the CPU time, which is certainly striking. So it's not a slight difference, it's an enormous difference. And with the tolerance 10 to minus 10, you have more than 1,000 seconds, so more or less 20 minutes, something like that. And instead, you have 1/10 of seconds if you use the fast linear algebra, because you add more than 1,500 ODEs. So what is the final message? Well, in this way, we can apply ODE and DDE solvers without doing anything more. This is nice, in particular if one is lazy and doesn't want to develop a completely new approach and also wants to combine very, very traditionally experimented solvers with this kind of problems. We can make use of variable step size strategies, which here is very important. The linear algebra, so the CPU time, is not really a big problem. The memory is a problem. The memory is a problem. You add additional ODEs. So if you have a partial differential equation, you certainly imagine that you have a system of dimension 1 million. You certainly cannot add 1,000 variable to any single variable due to a local integral term. So this should be certainly investigated if one is interested in this. What I did was for the gamma distribution, the Pareto distribution, so t to the minus alpha, you can certainly do something similar if you have a Laplace transform representation, ideally a real Laplace transform representation of the kernel, and you can apply essentially trapezoidal quadrature having spectral convergence. So you can repeat more or less the analysis we have done. Otherwise, one should study different strategies. But for the most important distribution that are used in pharmacodynamics, at least, we have seen that this is possible. Thank you very much for your attention. And if you have any question, please ask me. We submitted the paper to CISC yesterday. Oh. Our codes are available on our websites. So if you are curious or you want to try them, please take them. Feel free to take them or to write me. Okay. So I would like to interrupt the condivision. Did I interrupt the condivision? Yeah.
Here we are. We can see you now. So
okay.
Thank you, Nicola. It's time for questions. I check if there are online.
Yeah.
Pietro.
Can you hear me, Professor?
Yeah.
Great.
Yeah, thank you very much. It was quite interesting. And I was wondering if this methodology can be used for fractional viscoelasticity, because in viscoelasticity, actually the stress-strain relation, constitutive relation, is in form of a kernel integral type with memory. And so at the end of the day, it is one of the cases you show, actually, with the gamma distribution, and it's reduced to the fractional derivative, basically. And in that case, I remember that there was a numerical approximation which was called Grunwald-Letnikov approximation. But the problem there was that the history vector of the displacement, you had to consider it increasing in dimension. To build up all the previous history.
Yeah, exactly. This is the point here. Here you don't have any more memory because the memory is implicitly stored in the Z vectors. So this method is called oblivious, like it forgets that there is an integral operator. It can be used in the fractional problems. The most significant and the most challenging problem that might arise in this case is if you have many, because for any integral term that you have in my slide I had only one. Clearly there is no difficulty to write many terms in the right hand side. So if you have many terms in the right hand side, you can certainly use this. The memory doesn't increase because you don't have to approximate the integral anymore. It is fixed when you decide how to approximate the integral. But you have to add these Z vectors And if you want to be very accurate, these Z vectors have a dimension that increases this. And so if you have many Z vectors, then you have again a storage memory storage problem. But indeed, I would be very interested to study the application to fractional equation. So I would be grateful if you indicate to me details on this problem.
Sure. Because at the end of the day, in 3D problems, in solid mechanics, you have a stress vector or tensor, let's say, which is symmetric but has 6 components. So for each of the components, you have a fractional evolution equation, and this gives you 6 times what you said in your, okay. It's clear.
Yeah, I think it would be very interesting to see this, and certainly it is not a trivial extension, it's a challenging problem. But I think that there is potential for this, because if I understand correctly, the problem in their approach was to the fact that when time increases, you have a longer and longer memory.
Yes, exactly. Yeah, exactly.
This is forgot. Here is that we don't have this.
Yeah. Great.
The internet disappears. You just see a system of ODEs with fixed dimension.
Thank you very much, Nicola.
So if you send me, I'm very grateful. We can discuss it.
Sure.
Thank you to you.
Thanks.